Hey guys, in this video I'm going to be going over the third question from the 2008 AP Calc BC FRQ. And before we get into this, this problem is based on Taylor series and Taylor polynomials, so let's just review those before we begin. Taylor polynomials follow the format Tn equals f of a plus the first derivative of f of a times x minus a plus the second derivative of f of a times x minus a squared over 2 factorial plus f third derivative of a times x minus a to the third over 3 factorial, and it goes all the way to whatever n is. Now, it should also be important to know what Maclaurin is, and Maclaurin is the exact same as Taylor, except a is just 0, so it would be f prime of a times x, a second derivative, times x squared over 2 factorial, and so on like that. And something else you need to know is Lagrange error, and that's m times absolute value of x minus a to the n plus 1 over n plus 1 factorial. And basically what you want to do with the Lagrange error is maximize what m and the absolute value of x minus a is. And m is usually the next derivative from your previous term. So basically Lagrange error is, well, usually it is the next term in your Taylor series. Now that we've reviewed, let's get into this problem. So it says that let h be a function having derivatives of all orders for x greater than 0. Selected values of h and its first 4 derivatives are indicated in the table above. The function h and these 4 derivatives are increasing on the interval 1 to x. So part A says, write the first degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. Is this approximation greater than or less than h of 1.9? Explain your reasoning. So let's split this problem up into 2 parts, A1 and A2. To do A2, you need to do A1 first. So to write the first degree, what you do is follow the formula as I showed you before. So it's 80 plus 128 times x minus 2. Now, you want to solve for h of 1.9. So you just sub 1.9 in for x. So 80 plus 128 times negative 0.1. Now, this question is a calculator okay problem. So let's just plug it in. 80 plus 128 times negative 0.1. So the answer is 67.2. And that's the approximation. Now, is this approximation greater than or less than h of 1.9? Well, let's see. If you look at the second derivative, it's greater than 0. What does this mean? So if h prime of x is greater than 0, that means h of x is concave up. If a function is concave up, that means any approximation is going to be less than the actual value. So therefore, approximation of h of 1.9 is less than h of 1.9. Now part B, write the third degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. So part B is basically part A, except you go up to the third degree. So 80 plus 128 times x minus 2 plus 488 over 3 times x minus 2 squared over 2 factorial. When you get to the squared, it's important to remember that you have to write the factorials, because most people, or at least I, would forget to write the factorials while I was doing the problem, and I lost some serious points because of that. So it says go up to the third degree, so we'll go one more step, 448 over 3 times x minus 3 cubed over 3 factorial. And use it to approximate for 1.9, so of course h of 1.9 is roughly whatever, and you just plug 1.9 in for x. So the answer should be 67.988, remembering to go up to 3 decimal places. Now part C is use the Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with error less than 3 times 10 to the negative fourth. Now you're probably wondering, oh my god, Lagrange error. Well, Lagrange error is actually really easy. Lagrange error is m times the absolute value of x minus a to the n plus 1 over n plus 1 quantity factorial. Now n plus 1 is just the next term, so when it asks for third degree, you go up to fourth degree. The fourth derivative of h is 584 over 9. Then you plug in x, so 1.9 minus 2, and this is to the fourth degree, and this is all over 4 factorial. And if you solve for this, it is 2.704 times 10 to the negative fourth. Now, this value is less than 3 times 10 to the negative fourth. So the Lagrange error bound estimates with error less than 3 times 10 to the negative fourth. And that is all for this FRQ.